a very important method in protein chemistry. So we get more information about the structure and function of protein. So that's the reason why this guy, Kurt Woodtree from Switzerland, I guess, yeah. So he was awarded Nobel Prize in Chemistry, yeah, in 2002 for his development of NMR spectroscopy for determining the three-dimensional structure of biological macromolecules in solution, yeah. So the Nobel Committee need to put that word in solution because this method is different from the X-ray, yeah. And the main difference is we see the movement of molecule in solution. So that's why it's stated there by the Nobel Committee. Yeah, it's very important discovery. Yeah, and NMR is not used just to see the structure of protein. Yeah, even one of the application of NMR is to see what happened in your body. Yeah, but they changed the name. It's not NMR anymore. They changed the name into MRI. Yeah, maybe you heard this word MRI, yeah, magnetic resonance imaging, and these people, yeah, Paul Letteber and Peter Mansfield, they were awarded Nobel Prize in Medicine in 2003, yeah. So 1 year after, yeah, 1 year after, they got Nobel Prize in Chemistry for the discovery of MRI. MRI actually is NMR, yeah, it's NMR, but the difference is they don't use the word NMR, yeah. Why? Because the word nuclear, it scares people off. Yeah, they want to avoid the use of that word nuclear. Yeah, because when you go to hospital and then doctor tells you that, oh, we need to scan you using nuclear magnetic resonance, people get scared, you know. So they change the word. They change the term into MRI, yeah, magnetic resonance imaging. Yeah, so it's more pleasant to hear. Yeah? Magnetic resonance, but basically it's NMR. Yeah, and the difference is in NMR, the sample is chemical. Yeah, but in MRI, the sample is you. Yeah? The sample is your body. Yeah, so you will be put in this machine. Yeah, so you are the sample. You will be put in MRI machine, and the MRI machine will see the movement of molecules in your body. Yeah, especially those with water molecules in it, because MRI detects the hydrogen. Yeah, it detects the proton. You learn from CHM 3402 that proton NMR detects the hydrogen. Yeah, so plenty of hydrogen in our body. It comes from mainly from water molecule. So using MRI, if something wrong happened in your body, so it affects the concentration of water in that cells or in that organ, so it can be detected. Yeah, so your body, if you have some medical issue, MRI will give you different image compared to healthy body. Yeah, so by looking at the difference, doctor can say, well, something wrong with this organ, you know, and then okay, so in order for us to know more, let's do surgery. Yeah, let's open and see the organ. Yeah, but to detect the problem in your body, you need to do MRI. Yeah, to locate where the problem is. Okay, so it's very important discovery in medicine. So yeah, it's a Nobel Prize discovery. Yeah. So NMR is useful in research. Yeah. In organic chemistry, people who are doing organic chemistry, they should know how to interpret NMR spectrum. Yeah, you learn in CHM 3402. In protein chemistry, it's a very important tool to see the protein structure, and also in medicine, it's very important tool. Yeah, it's a main tool to see what happened inside your body. Yeah. So, and however, there is a problem. Yeah, there is a problem. Yeah, as you can see here, even though NMR gives you a lot of information about protein structure, but if you see in Protein Data Bank, yeah, I hope you still remember this database. I show you this in my introductory lecture, that about protein data bank. Yeah, it's a database of protein structures. Yeah, so the protein structures that come from NMR, it doesn't really grow year to year. It doesn't really grow in terms of quantity. Yeah, as you can see here, I think the NMR structure is the dark blue one. Yeah, so compared to X-ray, yeah, X-ray I think is the rest. Yeah, X-ray is the rest. Yeah, so NMR is the dark blue one. So it doesn't really grow. Yeah, there is a problem. There is a problem why NMR is not preferred. It's not preferred to get the structure of protein. There is a problem with it. Yeah. So when you compare with X-ray, of course, X-ray is still the most preferred way to see the structure of protein. Yeah. There are many reasons. Yeah. Just to repeat what I told you in my introductory lecture. NMR is expensive. Yeah. The machine is expensive. The method is expensive. And to get the result is not easy. Yeah. So that's the reason why not many structures obtain using NMR. Yeah. But X-ray, the method is cheaper. Yeah. And faster to get the structure. Yeah. Relatively easier to get the structure. So that's why more structures are obtained using X-ray than using NMR. Yeah. Yeah, so this is the reason why, the first reason why getting structures from NMR is difficult. Yeah, because of the complexity of spectra. Yeah, I'm sure you are familiar with the spectra. With this this spectrum is from alcohol, from ethanol. Yeah, so if you have this structure, it's very simple. Yeah, ethanol is very simple molecule. So that's why if you look at the spectrum, it's very simple as well. Yeah. So you can easily say, well, this peak belongs to methyl, this peak belongs to CH2, this peak belongs to OH, because you have only two carbons, six hydrogens, and one oxygen. But what happened when you have this protein? This is very small protein, you know, very small protein, BPTI. Yeah, BPTI is very small protein. The molecular weight is only 6,500. With this very simple protein, the NMR spectrum that you get is like this. It's very difficult for you to identify which is which peaks belongs to which hydrogen. Very difficult. It's almost impossible. Yeah. So this is folded. And another issue is the NMR spectrum of folded structure is different from the NMR structure of unfolded structure. Yeah, RC is random coil. When you open the structure of the protein, when you denature the protein, the spectrum will be different. Yeah, so the spectrum is very complex, one, and then the spectrum is also not consistent. It depends on the conformation of your protein, whether the protein is folded or the protein is unfolded. Yeah, too much overlap. Yeah, too much overlap. You cannot easily assign which is which. Yeah. Right. And yeah, the machine itself is pretty expensive. Yeah, I think the machine now is around 5 million ringgit. It's very expensive. Yeah. And also, this is the spectrum. Yeah. To get a clearer spectrum, normally people use two-dimensional NMR. Yeah? Two-dimensional NMR, which I will show you today. Yeah. So to increase the resolution, yeah, to separate the peaks better, so they use 2D NMR. Yeah. It's very expensive because you need to label the protein. You need to label the protein. Yeah. By using 15N and 13C. All right, and it's not easy. It's expensive. It's not easy because if you observe the hydrogen, the spectrum will be very complicated. Because what? Because when you observe the hydrogen, you get splitting. Yeah, because still remember your CHM3402. Yeah, when you run a protein NMR, when you run a proton NMR, yeah, hydrogen NMR, The information that you have is the integral, yeah, the size of the peak. It tells you how many hydrogen you have, yeah, and also you get splitting. You get splitting, right? Splitting tells you how many hydrogen your neighbor has. Yeah? How many hydrogens your neighbor has. So it has information about that particular hydrogen, and also it gives you information about the neighboring hydrogens. Yeah. So in protein NMR, normally we don't use a proton NMR, but you use carbon. Yeah, because in carbon NMR, yeah, I hope you still remember in 3402, you don't get splitting. Yeah, you don't get splitting. Yeah, what you get is one carbon. For each carbon, it gives you one peak. Another carbon which gives you one peak. No splitting. Yeah, so the spectrum is easier to see. It's easier to interpret. Okay, so that's the reason why we have to label it with 15N, 13C. That's the isotope of carbon and nitrogen, but it's very expensive. Yeah, and it's not easy to get. Sometimes you don't get anything. Yeah, sometimes you don't get anything because it's unnatural. Yeah, so sometimes, oh well, you don't get anything because it is unnatural. Yeah, so but the information is a lot. Yeah, you can see the movement of the protein, as you can see here. The protein is moving. When you superimpose the structure of proteins, you can see how the protein moves. Yeah. But again, it's very expensive. All right. So today I'll show you how to use NMR to see the structure of peptide. Yeah. So peptide is small protein. Yeah. So I'm not going to discuss about protein NMR because protein is big. We are going to see the peptide NMR, yeah, because peptide is smaller, so it's easier to see using NMR. Yeah? So when you do NMR on peptide, you can use a proton NMR, yeah. So we call this as a proton NMR, yeah. And by using NMR, you can actually identify individual amino acid using this method called COSY or TOXY, yeah, COSY and TOXY, yeah. And also you can see the connection between amino acid, yeah. We call this method as NOSY or ROSY, yeah. So you see you can identify the individual amino acid, and you can see the connection between amino acid, yeah. So you see the sequence, yeah. Which one is the amino acid number 1, which one is number 2, which one is number 3, and etc. Yeah. All right. So yeah, so this is a typical NMR spectrum of a peptide. Yeah, a lot of overlap. Yeah, the peaks are overlapping. Yeah, it's very complicated to interpret. Okay, so methyl protons normally will show up around this, around 0 to 3 ppm. Yeah, and H alpha. Yeah, H alpha. If you go back to the structure of the peptide, you know where C alpha is. Yeah, C alpha is here. This is C alpha, right? And then the hydrogen that attached to C alpha is called H alpha. And water always come up at the center of the spectrum, very huge peak, yeah. And also the backbone NH will come up around here. Yeah, this is the backbone NH, all right? Okay, so if you have an aromatic group, your aromatic protons will come up here, yeah. So yeah, this is a typical NMR spectrum of a peptide. It's very complicated, yeah. And the biggest issue is water, yeah, because water peak is huge, yeah. It comes from the OH, yeah. In CHM 342, you learn that when you have OH, then the peak is huge, yeah. The peak is wide, so it covers some of the important peak here. So normally when we run a protein NMR or we run a peptide NMR, instead of water, we use D2O, yeah, D2O, okay. We call it as deuterated water because D cannot be seen in NMR. But H2O, yes, can be seen in MR because it has hydrogen. But when you replace H2O with D2O, you can remove water peak. Yeah, you can remove water peak. Okay. It's you can buy this. Yeah, you can buy this. It's just like water. It's just like water, you know. So you dissolve your sample using D2O. Yeah. Okay. Right. So because the peak is so complicated, yeah, it's so complex. So normally we don't rely on 1D spectrum only. Yeah, this is one-dimensional spectrum. We don't rely on this only. Otherwise, you will not get anything from this spectrum. Normally, we run two-dimensional NMR. Yeah, so two-dimensional actually is this is 1D. This is the same 1D, and you find the cross peak. Yeah, the cross peak. Yeah, so the cross peak tells you which peak can see which peak. Yeah, which peak can see which peak. For example, this peak. This peak could probably belongs to the, you know, one of the amine group, yeah, NH. It can see itself. Yeah, it can see itself. So you can see this cross peak. Yeah, this one, it can see itself. So you see this cross peak, right? And then the second one, of course, it can see itself. So you see another cross peak. And then this is the blue one. Blue peaks, it will see itself as well. You get another cross peak and another cross peak from this red one. Yeah, because this red one can see itself. Yeah, another cross peak, cross peak, cross peak, cross peak, cross peak. So you can see a diagonal cross peak when each proton sees itself. Yeah, that's one thing. But of course, the most important information is this proton can see their neighbor. Yeah, this proton can see their neighbor. For example, this cross peak. Yeah, this cross peak comes from this blue peak that can see this yellow peak. So this yellow peak and this blue peak, they can see each other. It means what? It means they are in close position, in proximity. Yeah, they are in close position because they can see each other. From here, we can guess the structure of the peptide. Yeah, because when they can see each other, it means their position is pretty close. Yeah. What else? This cross peak. This cross peak comes from this red peak. Yeah. This peak see each other with this peak. All right. And then this cross peak. Yeah. It comes from this peak that can see this peak. All right. So the same thing here. Yeah. The same thing here between this and this. Okay. So these cross peaks are very important because it tells you that two protons are close each other so they can see. Yeah. You remember this thing, right? J coupling. Remember that from CHM3402, J coupling. When you have two protons and they're pretty close, they can see each other. Okay, in one molecule. Yeah, in one molecule, you see proton separated by 3 bonds. We call it as 3J. When they're separated by 4 bonds, we call it as 4J coupling. Yeah. So if you forgot, go back to your HM3402 and then read again. Okay. What information we can get by looking at this cross peak? We can identify the amino acid. We can identify what amino acid we have in the peptide. Yeah. For example, this is aspartic acid, and this is the structure. Okay, this is the structure. So, in aspartic acid, This proton, yeah, we call it as amine proton, yeah, proton that is attached to N, can see this alpha proton, yeah. It's a 3J coupling because these two protons are separated by 3 bonds, yeah, 1, 2, and 3, yeah, 3J coupling. And as a result, we see cross peak here, yeah, because they can see each other, yeah, Hn and H alpha, they can see each other. So one cross peak here. What else? This Hn can also see H beta, yeah. There are two H beta 1, H beta 2, yeah, that is attached to C beta. So you can see cross peak here, yeah, between Hn and H beta 1 and H beta 2, yeah. And at the same time, this hydrogen alpha also can see the hydrogen beta, 3J coupling, yeah, because they are separated with 3 peaks, with 3 bonds, yeah. So this H alpha will give cross peak with H beta, yeah, H beta 1 and H beta 2. And of course, H beta 1 will see H beta 2, 2J coupling, yeah, 2J coupling. So you can see this peak, cross peak between H beta 1 and H beta 2. So when you see these cross peaks, this is specific for aspartic acid, yeah. So the pattern is specific for aspartic acid. That's how we identify the amino acid using NMR, by looking at the pattern of the cross peaks. All right, second amino acid, phenylalanine. This is bigger, yeah, and more complicated, okay. So what happened here, the Hn, yeah, H hydrogen that belongs to nitrogen, can see H alpha, of course, yeah. It's a 3J coupling because they are separated by 3 bonds. So you can see cross peak here between Hn and H alpha, yeah. What else? This Hn can also see H beta, yeah, H beta, and you see there are 2 cross peak here, all right. And one thing that differentiates phenylalanine and aspartic acid is that the presence of aromatic group here, yeah. It's a delta, yeah, and gamma, yeah, delta and gamma, right? Delta and gamma proton, and because it's too far from Hn cannot see them. Hn cannot see this proton, cannot see this hydrogen. Therefore, this hydrogen, they will come up with their own cross peak here. See this? Yeah. They see each other. They see each other, but Hn, H alpha, and H beta cannot see them. Okay. So when you see this pattern, you know that in your peptide you have phenylalanine. All right. So this is the why Kootwootri is very genius, yeah, and he got Nobel Prize for that, because he can see the pattern for each amino acid, yeah. Instead of looking at this very complicated spectrum, Kootwootri look at the pattern for each amino acid, yeah, and he come up with this. Each amino acid has its own pattern, yeah. This is glycine, yeah. The cross peak pattern is like this because it's very simple, yeah. It has only only 2 hydrogens. One belongs to N, one belongs to C alpha, yeah. Alanine as well is very simple, yeah. Valine, isoleucine, leucine, tryptophan, and etc. Okay, so yeah, this is this pattern was first recognized by Kootwootri, yeah, and he wrote a book, NMR of Proteins and Nucleic Acid. It's a very classic book, yeah. So everybody's doing NMR, they must have this book, yeah? So he put the pattern for each amino acid. So this is the pattern, So he made NMR spectrum very simple to understand. Yeah. Why some people are genius? Some people are genius not because they make things complicated, no. They are genius because they make things easier to understand. Like Woodtree. Yeah. He simplified the way we see NMR spectrum by discovering this pattern. Okay. Albert Einstein. He's genius because he can condense the complexity of a nature, yeah, into one equation, which is relativity. All right. So that's how people are called genius, because they make things simple. People are not called genius by making things complicated. Okay. So by making things simple. Yeah. And this is called fingerprints. Yeah. So between 1 to 5 ppm, yeah, each amino acid has its own pattern. Yeah, for alanine, yeah, it has 2 dots here, around 1.5 and around 4.5. Yeah. So cysteine, aspartic acid, glutamic acid, and etc. Okay. So by combining this pattern and this pattern, you can actually identify what amino acid you have in your protein or your peptide. Okay. Okay. So this is the actual spectrum from my work. Yeah. I did it in 2006, 2007. Yeah. So 13 years ago. This is the peptide. Yeah. It's a cyclic peptide. And this is the amino acid sequence. Yeah. It has lysine, proline, arginine, glycine, glycine, etc. Yeah. And this is the 2D spectrum. Yeah. We call this as 2D toxi spectrum. Yeah. 2D toxi, two-dimensional toxi. All right. Okay. So this is the region of NH. Yeah. And this is the region where we can see the interaction between NH and side chain. So by looking at these two white boxes, I can identify what amino acids I have in my peptide by looking at these two white boxes. Yeah, because I know this NH. I know the interaction between NH and side chain. Yeah, and by looking at the NMR spectrum pattern, yeah, that I showed you before, I can easily identify what amino acid I have in my peptide. So we call this region as fingerprint. Yeah, why is fingerprint? Because by looking at this region, we can identify what peptide, what amino acid we have in our peptide. Yeah, this is how I identify. I use a software. Yeah, so the software can identify the cross peaks. Yeah, can identify which peak interact with which peak. But 40 years ago, when I did my postdoc in the US, my advisor, he did NMR spectrum interpretation 30, 40 years ago. He used pen and paper. Nowadays, people use computer, but 40 years ago, people used pen and paper. So they print the spectrum in a piece of paper, and he used pencil or pen to draw this line, yeah, to draw this line to find the cross peaks. Yeah, so it's more difficult. Yeah, but now with computer, it's easier. So, and then I'm able to identify all the amino acid. Yeah, I'm able to identify this K, R here, E, V, T, etc. And G. Unfortunately, all these 3 glycines, they overlap. Yeah, these 3 glycines, they overlap. Okay, so I have to use a more sophisticated machine to get better resolution. Yeah. So yeah, I was able to identify all these amino acids. Yeah. All right. So that's the first information I get from NMR spectrum. Yeah, I'm able to see the amino acids. But the next question is, which amino acid connects to which amino acid? Yeah. So go back to the previous slide. How do we know that P comes after K? How do I know that R comes after P? How do I know that G comes after R? And which G? This is very complicated because I have 3 Gs here, 3 glycines. And which glycine is which? Because 2 glycines are here and 1 glycine is here. So I need to find a connection. I need to find their position in the peptide sequence. How do I know that this L is located between this V and this V? How do I know? To know that, I need to run another experiment called NOESY. Yeah. So we have TOCSY, and now we have NOESY. Yeah. Or sometimes people call it ROSY. Yeah. I like to use the word ROSY. Yeah. NOESY or ROSY. Yeah. So by doing this experiment, yeah, NOESY or ROSY, we can see the sequence, yeah, of the amino acid through space correlation. Yeah. So from one amino acid, this is one amino acid, we can see the connection with the next amino acid. This is next amino acid. Okay, so this is amino acid number 1, this is amino acid number 2, and by doing NOESY or ROSY, we can see the connection between these two. Yeah, between space, yeah, through space correlation. Okay. So, yeah, so this is the difference. Yeah, this is TOCSY. Yeah, we run TOCSY to see the amino acids. Yeah, what amino acid we have in the peptide. And NOESY, we see the sequence. Yeah, we see the sequence. For example, we have leucine, we have alanine, we have asparagine, we have glycine. From TOCSY, we know that. We know the amino acid. But how they connect each other? We see the correlation. We see the cross-peak between them. Yeah. For example, we know that leucine and alanine, they are next to each other. Because what? Because we can see the cross-peak here. And we know that leucine and glycine are next to each other. Why? Because we can see the cross-peak here. We know that alanine and glycine, they are not neighbor because there is no cross-peak between alanine and glycine. That's how we identify the sequence of a peptide or protein, yeah, by looking at the cross-peak using NOESY experiment. Yeah, so still the same peptide that I use, yeah. The red one is TOCSY, yeah. The previous experiment, the red one is TOCSY. The green cross-peaks are NOESY, yeah. So from green one, we can see that the connection between red peaks, yeah. Red dot, this red dot, it has a correlation with this red dot, so they are next to each other. Yeah, so you can see the green peak here. Another green peak here is between this and this. Yeah, so they see each other. Yeah. All right, and also from here, we can see the connection between amino acid. Yeah, and even I can put the number here. This K is number 1, is amino acid number 1, and then amino acid number 2, proline. Proline cannot be seen in NMR, unfortunately, because it's very flexible. Yeah, it cannot be seen in NMR. Yeah, and then arginine number 3 is here. Number 4, 5, 11 is here. I was able to separate them and see them clearly, yeah. And then number 9, number 8, 6, 10, 7, and 12. Awesome, yeah. And see all these red dots, green dots, that's a correlation, yeah. There's a correlation between amino acid number 1 and amino acid, the next amino acid, yeah. Okay, so why we use NMR? Yeah, why we use NMR? Because by doing NMR, we can see the three-dimensional structure. Yeah. Three-dimensional structure. Not only the connection between amino acid number 1 and number 2, number 2 and number 3, number 3 and number 4, number 4 and number 5, number 5 and number 3, number 6, no. Look at this. Even I can see the connection between amino acid number 6 and amino acid number 12. Yeah, they see each other. Even though in the sequence, their position is not next to each other, no. But number 6 and number 12, they can see each other because they're close. Yeah. So from here, we can get the three-dimensional structure. Yeah, we can get a three-dimensional structure. So look at this. This is amino acid number 1, number 2, this is, I believe, is number 3. Yeah, number 3, 4, 5, 6, 7, 8, something like that. All right. Yeah, this is small peptide. Yeah. So, yeah. So from here, we can see that 1 can see 2 for sure. But as we can see here, 4 can also see 6. Because even though in terms of sequence, they are not neighbor, but in terms of three-dimensional structure, they can see each other. This can be detected in NMR. Yeah, I believe you learned this in CHM 3402 as well. Yeah, that even though the position in terms of sequence is not next to each other, but in three-dimensional structure, they can see each other. Therefore, they give NMR signal. In order for us to know that, I run another experiment. Yeah, we call it as a T-dependent experiment. T is temperature. Yeah, so I changed the temperature from 298 to 323. Yeah, and then I observed the changes in terms of chemical shift for each amino acid. Yeah, so I have amino acid 3, 4, 5, 6, 7, 8, and I increase the temperature. Yeah, stepwisely from 298 to 323, and I can see that their chemical shifts change. Yeah, their chemical shift change. Yeah, you see this, right? And I measure how fast the changes. Yeah, by measuring the slope. Yeah, how fast. Yeah. R3 changed a lot. Yeah, because the slope is the most. Is the highest. Yeah, minus 14. Yeah, but G4 and G5, they don't really change. Yeah, they don't really change even though I increase the temperature. What does it tell me? It tells me that they stabilize each other. Yeah, they hold each other. They stabilize each other through this interaction. Yeah, through this interaction. Therefore, when I increase the temperature, they don't change much. But the rest, they change a lot. Yeah, so it tells me that they have this kind of interaction. So by knowing this interaction, I know that they have this turn structure. Yeah, this turn structure. And this turn structure is very stable. Even though I increase the temperature, their chemical shift don't change. This is ROSI analysis. Yeah. Previous one is a TOCSI analysis, and then I continue with ROSI or NOSI analysis. Yeah. And in NOSI analysis, I can see the interaction between two amino acids that are located far from each other. Yeah. And even I can measure the size of the peaks. Yeah, I can measure the size of each peak. This is small peak, this is small peak, this is big peak, you know. And by looking at the size of each peak, I can see how far or how close they are. The closer they are, the bigger the peak is, yeah, because the interaction is stronger, the peaks become big, yeah. But if they are far from each other, the peak becomes small. Look at this green peak. The bigger the peak, the stronger the interaction is. The smaller the peak, the you know, the smaller the peak, the more far their interaction is. Yeah. So this is the size of each peak. And from here, using this equation, we call this equation as Karplus equation. Yeah, Karplus equation. Karplus equation. I can get their distance. Yeah, amazing. I can get their distance. Yeah. So this is the distance between amino acid number 6 and 4. And this is the distance between amino acid 3 and 4. This is the distance between amino acid 4 and 5. Yeah. So I have this long list of distance between amino acid. 3 to 3, 3 to 3, 6 to 6. Yeah. They interact between each other. Yeah. Among each other. Yeah. 7 and 8. What else? Let's see whether we have interesting. Yeah. 2 and 3, 4 and 4. Yeah, mostly it's among themselves. Yeah? So I get all this distance. Yeah? And also by using this equation, yeah, I can convert the 3J coupling into the angle, yeah, phi and psi angle. Still remember my first lecture, yeah, phi and psi angle. I can calculate phi and psi angle using 3J coupling, yeah. So this is the angle that I got from 3J coupling, yeah. And the end result is I got the structure. Yeah, I got the structure. So for this peptide also I run the temperature dependence, and I can see that the peptide number 1 and then number 3, they interact each other very closely. Yeah. And also I run the Karplus equation to see the peaks. Yeah, interesting here. Amino acid number 1 and number 12, they interact. Yeah. 7 and 6, they interact. So it's quite far. 4 and 12, jauh is quite far, but somehow they can see each other. Yeah, they can see each other. So we know the structure is U-shaped structure like this. Yeah. So number 4 and number 12, they can see each other. All right. Yeah, these all are the distance. Yeah. And also I did coupling constant. I converted to angle. Yeah, I got the angle, and I got the structure. Yeah. Yeah, that's all for the first part of my lecture. Any question before I continue with the second part? No question? No question? Either you understand or you don't understand at all.
Understand, doctor.
Okay. All right. So let's take a break. Yeah. So maybe 10 minutes. Yeah. We continue at what time is now? Yeah, we continue at 11. Yeah, 11 o'clock. All right. Okay. I'll see you.